Hello and welcome to the second video on compiler design. This time we're going to look a little bit at parsing and explain how the parser that I've started to implement works. And finally we'll add some additional parsing capabilities. So in particular we're going to add attributes to the grammar so that you can annotate declarations with custom attributes or attributes that say things about linkage or things like that. So first of all, as a small introduction, I'm going to restate the goals of this series. The goal is to create a compiler and explain the steps that I have to take to do that. And so in the process, I'm recording videos that correspond to each and every one of the steps, or major steps, let's put it like that. So right now, in terms of code, I've coded a little bit of the parser and I've changed a little bit the lexer. So in particular, what's important is I've added a lot of tokens. As you can see here, compared to the previous version, there's way more tokens for each and every symbol. I've added a lot of keywords, and I've also changed a bit the API to have types represented with camel case instead of using snake case, which I think is a good choice because it distinguishes between types and variables without having to add always the prefix union or struct in front of the type names. And second of all, if you look at the lexer, you're going to see that I've added code to parse literals. So this is for literals. This is for integer and floating point literals. It works by looking at the next character and determining whether this thing is a digit or not. And if it is a digit, then you skip the first digit. You essentially eat all the digits, including possible prefixes like prefix like B to indicate a binary literal, or X, or just a 0 that would indicate an octal literal, just like the C grammar. And then you would essentially skip all the digits that follow until you reach a dot. And if you reach a dot, you eat the dot and then skip digits again to parse the fractional part. Then you look for the E sign for the exponent, then accept the sign, and then again skip digits. So it's essentially very simple. And once we've skipped all the characters, we can just use the standard library functions to transform that into numbers like doubles or integers. The other part, so this is for identifiers. I think the last video was covering this, but the other part is that I've added comment escaping. So if you look at this, there's a thing to look for comments, which is this. And it's a slash sign, and if you see a slash followed by another slash, it's a single line comment, just like in C. So you have some code here to skip it. And if you see a star following a slash, then you know it's a multi-line comment. And again, you need to skip until you see, you skip all the content that you see in the file until you see another star followed by another slash. And if you don't see anything else, then it could be either slash equal, which is divide equal, the symbol that you use to divide something and assign at the same time. Or it could just be a slash alone, for which we just return, well, the division sign, the slash. Well, of course, there's also string literals, as you can see here, and character literals, but essentially it's just more content to the lexer. And that's it, basically. Nothing really groundbreaking. But so before we talk about the parser itself, I thought it made a little bit of sense to talk about the grammar and the language and what we actually want to parse here. So as an example, I've written a small test file here, which represents what kind of language we want, well, the kind of language we want to have. So I want to have the concept of a structure, a little bit like C, but closer in terms of syntax to what Rust does. So what I want to have is struct here, followed by the name of the struct. Then optionally, I want to allow the use of generics. Generics are introduced with the square brackets. Then a list of names like T, U, something like this. And then an open brace to indicate the beginning of the body of the struct. Then the members of the struct, like essentially just names, field names, like foo, for instance. And then a comma if you want several of them, like foo and bar. And then a colon sign to indicate that these things have a type, and then we write the type here, for instance, I64. And then to separate these things, I need another comma here to say, well, there's another group of fields, and this is it. So this will be the syntax for structures. As you can see, this allows to do this, x, comma y, comma z, colon t. And this syntax here is not allowed in Rust. So in Rust, for instance, you would have to do x, t, y, t, and z, t. It's not really important, but it's a nice thing to have, I think. And then I also want to have the concept of an enumeration, but unlike C, I want these enumerations to carry a value. So I'm closer to the concept of enumeration that you have in Rust, or what you have as sum types in Haskell or things like that, where you can have either just an enumeration value or an enumeration value carrying a value or an enumeration value carrying several values. So C here is an enumeration value that takes true integers so that you can do something like faz.c or just C, but you cannot just construct it without anything. You have to give arguments to it. Something like that. Then ideally I also want to be able to nest definitions. So I want to be able to do something like this: struct within a field. So struct foo, and then for instance something like this I32. That essentially means these two fields have this type which I'm just declaring right now. And if I want to refer to the type that is inside the other structure, I would have to do bar instantiated with the correct type arguments, like I32, I64 for instance, dot foo. That would be the type that would be there, essentially. And then I also want to have type aliases, like this. Type foo is equal to bar, which is just an alias, but I may want to make this, polymorphic or generic. Sorry. And for instance, I could do this. Foo is just var with t and t. And as you can see here, there's something that is repeated here, in that all these type definitions, they start with a keyword, here struct or enum or type. Then there's a name called bar, vec3, faz, or foo. And then there's a list of type parameters. And this construct is important. This repetition is important because it's consistent. So that's one of the goals of the language, to be consistent so that it's easy to understand and easy to change, and also easy to parse, because the more consistent it is, the more I can reuse parts of the parser. So it's beneficial essentially on every side of the programming language. Then I also want to allow the definition of constants, like this, where you just say const, followed by the name of the variable, followed by the initialization of that variable. And for constants, the initialization is mandatory. So you don't have to annotate the type, because the type of x here is defined by the type of the value. So type inference will be able to figure that out. But right now we're not considering this because it's only about parsing, but later on I will explain how this works. It's really, really simple. Then there's functions. Again, pretty similar. We have a keyword, the name, and an optional list of type parameters, something like that, if you want a generic function. Then a parameter list, actual parameters with names. And as you can see, similar syntax as what you have for structures. It's what I'm calling a pattern. I'm going to explain what a pattern is a bit later when I explain the grammar. But essentially, the parameter is just a pattern with I, J, and K as names in the pattern, and the types of these names are I8, which is just an integer of size 8, F32, a floating point value of size 32-bit, and then an array of booleans whose size is either dynamic or static, and the compiler should determine that for you. And then I also want to have pattern matching, so you're able to do something like this, match something with some other thing, and then associate depending on the value of the argument that I'm passing here. So if I do, for instance, I have a value here, and I can do essentially if I is equal to 0, then I don't know, return 3. If I is equal to 1, then return 2. Something like this. And yeah, I also want to allow functions to be declared inline. So I want to support the syntax where you have g equals f, a function call here f123, but any expression would be acceptable here. So I can just do this, and that's essentially just a function, takes no argument and just returns 1. And very, very similarly to Rust, the return value of this function here is essentially just the last expression. So here's the match statement, which means that every value you put here, 3 for instance, or 2, these are the return value of the function. This will bring me to talk a little bit about statements and expressions when I discuss the grammar, but that's for later. And then Of course, I allow the declaration of variables either within the body of functions or outside of it, and it works very similarly to what we have here with const, and we can have any expression on the right hand side, but it's also optional, so you don't have to give a value initially. Now the problem is here that if I do this, then the compiler cannot determine the type of this thing, so I'm going to have to annotate it, for instance, like that. I can also declare several variables at a time by using a pattern, by saying something variable bar and variable foo I64. This allows me to declare two variables at the same time. But I can literally use any kind of pattern I want. So I could just do something like this. I could do, for instance, declare a pattern that is for arrays and do this. But because this is an array, this wouldn't type because bar and foo do not have the same type, and the elements of an array have to have the same type. So that would have to be either unannotated or the same type. So either I do this or I do that. Or I do this and I do this is an array of I32. Right, something like that. Anyway, so this is essentially for the example. I'm going to revert everything. Yep. And I'm also going to now go back to the introduction and talk a little bit about the grammar. So before I explain how to parse things, I think it's important to spend a little bit of time to talk about the grammar. The grammar of a language is a representation of that language. It's a set of rules that describe how to produce sentences in that language. And of course, because we're talking about programming languages, the term sentence here refers to a valid program. So you can look at a grammar as some form of recipe to produce the programs that are accepted by the language. Now it's important to realize that this is parsing and we're not going to deal with type checking and things like that. So the grammar will be able to produce sentences or programs that are in fact incorrect from a type checking perspective. For instance, parsing will not care about whether this thing types. It will not care about whether I'm doing something like var x is equal to 3 and then later on I'm doing x is equal to abc. This is not the purpose of parsing and will not be dealt with at this moment. It's important to stress that out, I think. Similarly, we also don't care about whether this thing was declared before. So if I redeclare a variable, even though that's actually disallowed, the parser doesn't care about this either. Alright, so now that I've explained this, the grammar is essentially this set of rules, as I mentioned before, and as a set of rules, there's two concepts. There's essentially the concept of a terminal and the concept of a non-terminal. A rule is essentially written as something like this. It's written like left equals right. And what you have on the left here is called a non-terminal. It is something that can yet be transformed into something else. R here might or might not be a non-terminal because it might be something that finally appears in the language, or it can be something that yet has to be transformed into something else because it appears as the left-hand side of another rule, like here, for instance, if I were to do this. So, as an example, consider a small language where I want to parse something like A, and then B. So what I can do to represent that language in BNF, so BNF is a language to describe languages. You can call that a meta language. It's a convention that we use as grammar writers to describe our grammars. So the way it works is, like I said, you have a rule, and the rule is written like I explained before. You have something like a rule that I'm going to name A, and I'm going to give a production for that rule, which is to say, well, I'm producing something for this rule. This rule produces something. So A is either what? A is either A, for instance, and I can repeat A as many times as I want. So I also want to accept A, B, and any number of A's and then a B. So if I do, for instance, A is equal to A, that gives me just one A. So I want to be able to have more than just one A. So I can do this, A, comma, A. As you can see, it's recursive. I'm saying that either A is just one A or it's more than one, essentially. Then I want to say that my language is not just a sequence of A's, it's a sequence of A's followed by a B. So I can just say it's an A followed by a B. And then I say the root of the language is B. That is actually not specified, but I can write it in text and say the root is B. then whenever I want to create a word or a sentence in the language, what I'm going to do is I'm going to look at the rule here, which is the root, and choose some option. So here there's no option to choose, right? There's only one. It's concatenating A with B. So what I have to do is, well, I say there's B on the right and then there's something on the left. And then I'm going to say, okay, what is this something I'm talking about here? Well, it's A. And then for A, I have a choice. Either I choose just one A, so I would have A. If I do that, then I'm done basically, because A is a terminal. It doesn't appear on the left-hand side. And that's it. I have my word. That means the word AB is accepted. Or I can choose to take the second option, which would be in this case to have a sequence of A's more with well, one more A. So I would have A, and then B. But then A is not a terminal, so I need to reapply the rule. Again, I would have to make a choice. So I could just do A, B, for instance, and that would give me the word AAB, which is accepted by this grammar, and so on and so forth. So essentially, this grammar describes the language that I'm talking about here in formal terms, but in a formal manner. In other words, I've literally just described the language in a way that everyone can understand without having to explain it with words. I've explained it with an actual notation that is universal, or at least has a formal meaning. But this notation is called BNF, or eBNF in fact, because BNF is the name of the language, but there's an extended version of it that allows symbols such as question mark or star. And if you know regular expressions, you know that question mark is in fact an operator that says this thing or nothing. So maybe this thing is here, or maybe this thing is nothing. So if I say it's a question mark, it could be either A or nothing. So if I want to allow, for instance, parsing just B and accept just B, I can do things like that. That would allow me to say, but either there's one A or there's no A. And as you can see, this combinator is just a shorthand. I don't need it. It's something that helps me when writing rules, but if I wanted to, I could just do something like this. That would have exactly the same effect. So in other words, it's something that helps me write in this BNF language, but it's not necessary, because BNF as it stands is enough to write grammars. Okay, so now that I've explained this, the question is, what are the properties of grammars and what do we care about here? It's important to know, if you've never heard about this, that there's a classification of grammars that has been established by Noam Chomsky. And this classification of grammars, so you may have heard of Noam Chomsky in another context. He's also a person who has political opinions, and he has very interesting views on politics, on linguistics, and on language theory as well. But here we only care about the language theory part, and in this context we only care about this classification. He has also done a lot more work on this. But what's for interest of us is this classification of languages. And in this classification of languages, there's 4 categories of languages. Without describing them in detail, the lowest one is the regular language one, which is number 4, regular languages, which you may have heard already, I think, from other, live videos or other exposure to other libraries or languages where you have a regular expression library. And a regular expression is just a representation for a regular language, which is why you have symbols such as question mark, star, and things like this. But essentially, a language that is regular can be parsed or analyzed or essentially detected using what we call a finite state machine. So what's important to know here is that this is simpler than any program. It's a very specific type of program. It's not like a general program. In other words, the problem of answering whether some sentence belongs to the language is not just decidable, it's decidable, and the only thing you need is this small program of this specific shape called a finite state machine. Now, this is not so interesting because regular languages, they're not expressive enough. They don't have the expression power that we need to create a programming language. So while they are useful because they literally represent a lot of small languages that correspond to, for instance, URLs or things like this, they're not really useful here. In fact, I would say to be completely correct, they do have some use here because we in fact already implemented the parser for a regular language when we implemented the lexer. Because the lexer is just a fancy regular expression matcher, which transforms things that we see in the input stream as bytes into tokens. And those tokens are essentially what we're going to handle in the parser. But the process of doing so, or of looking at these bytes and transforming them into tokens, is just what a regular automaton would have done. A finite state machine, in other words. But yeah, anyway, that's not enough for us. So we want to look at something a bit better or a bit more expressive, which is the category of context-free languages. In this category, we're going to need something an automaton that has a stack to parse them. We need something that has a stack, and that's basically it. That's basically it. We need some form of machine that has a stack. So because our computers have stacks, we're fine, and we can work with that. There's also category number 2, which is less restrictive and more expressive than context-free languages. It's the opposite of context-free. It's languages that have context. I'm not sure if it's called contextual. Or contextual grammars, maybe. Contextual grammars. But anyway, this is probably too powerful. And then there's something even more powerful than this, which is just general... in a general case, essentially, when you don't have unrestricted grammars, essentially. So these are sets. Sorry, there's a typo here. These are sets. So essentially, the set of unrestricted grammars contains a set of contextual grammars, which contains a set of context-free languages and and so on and so forth. So it's a kind of inclusion relationship you have between all these things. And the unrestricted grammars is too unrestricted from my point of view, in the sense that it's not really useful from a computer science perspective, because answering the question in general, of course, because you may have regular languages within unrestricted grammars, but if you are outside of those sets, number 2 and 3 and 4, there's a chance, or there's a possibility, that answering the question of whether or not a sentence belongs to the language, so whether it's not even about parsing here, it's about answering the question of whether something is inside the grammar or is accepted by the grammar. Doing that may be undecidable, and that's really problematic, because it means that you may just not be able to answer the question, in the sense that you would have to wait forever for your program to terminate, and you don't know if that means that it takes a long time to answer the question, or if it means that the thing is just not in the language. So indecidability is really a problem here. So you want to be in the realm of context-free languages, because otherwise you're going to have problems. It's still possible to parse contextual grammars, but it's annoying, and I recommend not doing that, because, like I said, it's annoying. So you probably want to stay in this context-free language realm, because it's practical. It's a good compromise, in other words. And in compiler design, I think it's a lot of the work is to look at good compromises. All right, so now that I've explained this, I want to look at the grammar for foo, which I've already written. I've written this in a document called syntax.md, which you'll find in the documentation directory here. So if I open it, this is what it looks like. I have this syntax here where I say the syntax of the language foo is divided in 5 categories. We have types, declarations, expressions, patterns, and statements. So I'm going to go over each and every one of these categories, but first of all, we have to realize that some terminals, like the things that are the result of parsing, are just the tokens that we're going to look at. So the terminals are essentially the things that appear on the right-hand side of the rule and do not appear on the left-hand side. In other words, these are the things that appear in the language that we are looking at. Just like the small characters A and B here, these are the terminals. Like this here is a terminal. And in the same sense, an identifier is produced by like, there is a terminal, or a character literal, a string literal, an integer literal, and so on and so forth. Plus all the symbols that I'm going to use in line inside those rules. So first of all, there's a path. A path is something like a sequence of identifiers with type arguments, optional, of course, with a dot to separate these things. So it could be something like A.B.C. And in between, I may have something like this. Something like this with I32, for instance. This is a path. And of course, it is here because I want to have structures within structures. So I want to have something like struct foo. And then I want to have maybe a struct bar. And maybe I want to do foo.bar to refer to the inner type. But yeah, you get the point, you get the idea behind this. So I think I can move on. The way it works is very simple, very similar to what we had before. A path is either just a path element or several path elements separated by a dot. And actually this is incorrect because here you would only have two. So it's a good point that I'm looking at this right now. A bit stupid of me though. So I would have to do something like this, correct it like this by saying that a path is either just one path element or a path element followed by a dot followed by more path elements. And then I would have to say what more path elements is just a path element followed by dot followed by more path elements, or just a path element. But that's a bit like redundant, isn't it? So if you look at this, you're thinking, yeah, maybe we should actually merge the two. So what I can do is very simple. I can say, well, the path is just a path element or a path element followed by another path. And that works just as well. So now that is handled, we can look at types. So types are essentially what appears when I have a type annotation or when I have a parameter with a type and things like this. The way it works is a type is either a path, because you may have a structure, or they're referring to an enumeration or something like this. A primitive type, a tuple type. A tuple type is just a set of types separated by commas. And then there's an array type, which is, as you've seen earlier, a type between square brackets, and a structure declaration or an enumeration declaration if the types appear in line. So a primitive type is either one of these things, which is a dative again, it's boolean, A8, U8, F32, F64, U16, I16, or I32, or U64, or I64. Now this is fixed. And then we have, after that, declarations. Declarations are what appears either within a block. So you can think of it, within a function, I can declare things. I can declare variables, I can declare other functions, and I can declare a variable or a constant. So declarations can appear there, but they can also appear outside of a block at the top level. So a declaration is either a type parameter, if it's just appearing within a type parameter list, or it could be a structure declaration, which has an optional type parameter list, followed by structure fields being just a list of structure fields separated by a comma sign. And a structure field is just a list of names, of field names, followed by the colon sign, followed by the type of all these fields. Like I said, it's something like this. The name, a colon, comma, sorry, another name, and then the colon, and then the type. So it's exactly this structure that we have here. Then I have an enumeration declaration, which is again enum followed by the identifier, followed by an optional type parameter list, followed by the list of options, and the options are essentially just separated by the comma sign, and each option is just either one identifier alone or an identifier followed by a tuple type. And as you've seen before, a tuple type is a set of types separated by the parenthesis. Then you have alias declarations, which are just type declarations that alias another type. I've explained this here. It's something like this. And again, we have type followed by identifier, followed by an optional type parameter list, followed by equals, followed by type, followed by semicolon. Then we have function declarations, very similar. We have either a function which has a body with an equal sign, or a function that has a body which is just a block. And the function itself is said to be something that starts with fun, then the identifier, then a type parameter list, then the list of arguments, and a return type, which is optional here. So you can say my function returns this, or you can just omit it and let the compiler infer it, and then the function body. In fact, I could simplify this further by saying it's a tuple pattern here appropriately. Because, well, tuple patterns have parentheses here at the beginning. Then we have expressions. Expressions are things that yield a value. Contrary to statements, statements do not yield a value, but expressions can appear essentially everywhere inside a part which expects an expression, like the right-hand side of the equal sign, or when you're part of a statement that is an expression. So for instance, there are statements like when you assign something to a variable, for instance, you say I is equal to 3 semicolon. That's in fact an expression embedded inside a statement. The idea here is that I've mirrored the precedence of binary operations in C so that people are not, too annoyed by a different convention. And that's also, I think, the convention used by many languages anyway, so it really makes sense to follow that. The important thing here is that if you have a tuple expression or a tuple type or a tuple pattern which has only one argument, you treat it as a parenthesized expression, otherwise you have problems. And finally, there's an ambiguity here in this grammar that's important to mention. Like when you declare a structure, if you have a structure called S, declare somewhere like string S, A is equal to I32, then you can declare a structure by saying I have a structure, an object of structure S, and it's containing, nonsense. It's for instance, it's a variable called X which contains a structure S with field A is equal to 1. So that's a valid declaration for a structure, and that's very similar to what Rust does in terms of structures. However, if you have something like this, what the hell? If you do S, if S, and then you have a field name here, for instance, like equal to 2 or 1, doesn't matter. You see that there's an ambiguity here, because this if statement here could be understood as, well, could be understood that if I'm looking at this if statement, I see that the condition starts with the symbol S, but S could either be the condition itself, or it could be just like in Rust, beginning of the construction for a structure. And I have no ways of knowing this until I reach the else case, which is kind of annoying. In fact, the else case could be missing altogether, and then I would be left with this, and I don't know what to make out of this, right? Because I could have, for instance, something like this. Right? And this can be understood as if S, so if this expression here, if S here evaluates to true, which by the way doesn't type, but we're not dealing with this at this point. So if S here evaluates to true, then assign 3 to B, but it could also be if S has a name alone, like S is equal to true, if S, then assign 1 to A, then assign 3 to B. As in, this is actually a block to this. And because there's no semicolon at the end, it's still valid, but the value returned is the value of B, just like in C. So there's this ambiguity. So what we do here is we have a special case to deal with conditions, which is a condition, non-terminal, which is just like the regular expression. And by regular expression, I mean the normal expression, not regular expressions as in the regular expressions that you parse, but you know what I mean. Essentially, it's just like an expression, except I omit structure expressions in them. So to start, we have an expression is an assignment expression, and I have to look at what an assignment expression is. An assignment expression is either a logic OR expression, or it's a prefix expression followed by equals, followed by another assigned expression. And the prefix expression is something that has a prefix in it, so minus, minus, plus, plus, minus, plus, or bang. And if it's not that, then it's a postfix expression. And a postfix expression is either a typed expression or a call expression, or a postfix expression followed by minus minus, or a postfix expression followed by plus plus. So there's a lot of options here to choose from, and what we have here is essentially that we can have some expression on the left hand side which does not have, which is not a binary expression essentially, it's either postfix or prefix, and then we have an equal sign, then an assignment, and then the assignment expression is yet again another one of these, or a logic OR expression. And a logic OR expression, it's badly named in a sense because a logic OR can be a logic AND, but you get what I'm trying to say. A logic AND expression or a logic AND expression ORed with another logic AND expression, which is why it's called a logic OR expression. And then similarly, the logic AND is either an OR expression or an OR expression followed by the logic AND operator followed by an OR expression. So you start to see a pattern here. You see that the rule here is either another rule or this other rule followed by the operator followed by the other rule. And if you look at this, it's basically the same for all these operators, and it follows the priority of these operators. In other words, by designing the grammar like this, I enforce a certain order. I enforce the order that some operator like multiply, as you can see here, has higher priority than plus. So that if I write a plus 3, so without the parentheses, multiplied by 3, it is not parsed as a plus 3 multiplied by 3, but it's parsed as a plus 3 multiplied by 3, as in like that, which is the expected convention for everyone, I think. And so the reason for this is, imagine I have an expression defined like this, as a small example. Imagine now if I were to define my grammar as saying expressions, something very simple of course, I could say an expression is just an expression multiplied by another expression. Or it's an expression plus another expression. Or a number, right? And a number being a 1, 2, 3, 4, 5, and so on and so forth. So if I define expressions like this, and I have 1 plus 1 multiplied by 2, then I can decide that this is produced by doing something like expression equals expression plus another expression, and then I can say then that the expression on the left is a number, so 1 plus another expression. Then I can say that the other expression on the right is a multiplication expression, so 1 plus expert multiplied by expert. And then I can say that this is 1, so just to show the priority here, 1 plus 1 times 2. So by doing this, I essentially do this, right? I parse in that order. This is how the rule is expanded, essentially, so that you see it clearly. Those parentheses represent how it's expanded. So this is actually good, right? This is what we want. But the problem is I can also do this the wrong way. I can start with multiply, which sounds weird, right? But it's totally possible. I can do this with multiply. I can say 1, in this case wouldn't be 1, it would be expert. I leave it like that, and I say the expression on the right is 2. Then I'm saying that this is another expression with a plus, and then leave the 2. So we transform expert into expert plus expert, which is fine, it's allowed by the grammar. And then we have 1 plus 1, that's also allowed by the grammar, times 2. And as you can see here, I've parsed this the wrong way. I'm looking at this the wrong way because now I have grouped operations in a different way. This is called an ambiguity. The grammar is essentially ambiguous in the way it describes this expression. I've made this expression, and now there's 2 ways to produce that expression from different paths. And now, in terms of production rules, it's not so much of a problem because the question that this grammar answers is whether the sentence belongs to the language, and the answer to that is yes, because even though there's 2 ways to produce it, there's 1 way to produce it, right? Because there's 2 of them, and because there's 1 way, then it means the sentence belongs to the language. But we're not interested in this. We are also interested in the actual way the rules are produced. This shows you that not only are the rules important from a question of whether the thing is in the language or not, but they're also important in terms of in which order you apply them, in which order they unfold, in which order you're going to produce some content. And that order is problematic if you don't do the right thing. So if you don't force a certain order, then you can produce things in the wrong way. So what I'm going to do here is I'm going to force an order. To prevent this from happening, I'm going to say I have two types of expression. So an expression is, first of all, an add expression, right? And an add expression is a null expression followed by plus, followed by a null expression. Or it's a null expression directly. Then I say a null expression is either just a number followed by a multiply sign followed by another number, or just a number. And if you look at this grammar, it's in fact equivalent to this one. They parse the same thing. They produce the same language. This thing, for instance, would be produced by that language. To show you, I can just take the second one, and I should call this x2 to make this clear. So if I take x per 2 is transformed into here an add expression. I don't have a choice. There's no other option for me to do this. It must be an add expression. So it must be then something that is either a multiplication expression or a plus between two multiplication expressions. So I'm going to choose the first one, null x per. Again, that's me choosing it. The production rules don't tell me an order. I know in advance which one it is, so that's why I'm choosing that one. But yeah, you get the idea. So this is what I'm left with, and then I'm going to have to say, well, the first null expression has to be a number. And the second one has to be a number multiplied by a number. But I'm going to do this like this for the moment. Actually, I'm going to write this in a much simpler way. I'm going to do this null x per plus null x per. And I'm going to do this like this. It's way more readable and easier to understand. Number plus another null expression. And then I'm going to say number plus number multiplied by number. And then I can finally replace the numbers, so we see that it's 1 plus 1 multiplied by 2. And this is the only way I can produce this. There's no other way. I cannot parse this by starting with something else than the add expression. Because if you think about it, here I don't have a choice. There must be a plus. Because once I go into the null expression, if I were to say, well, my add expression is a null expression, I can no longer place pluses. After I've entered the rule null expression, no pluses can appear anymore. So the plus has to appear before the multiplication appears. So I have only one way to do this, which is to go that route. So we effectively, by doing this small transformation, we effectively transform the languages into something non-deterministic, into something deterministic. It's an important transformation to keep in mind because it's essentially the basis of precedence parsing. So this is how these rules work, and like I said, this is a general idea behind all these rules, and I think you can trust me if I tell you that these things follow the precedence of C. The order in which I'm listing them is the same. So you start with the logic operators, then the bitwise operators, then the comparison operators, then the shift, then add, and then multiplication and division. So that's pretty much it. What's more interesting here is that I also have other types of expressions. I have an if expression. It's not a statement because in this language, just like in Rust, if produces a value. In other words, there's no ternary operator like in C. In C, you have a dedicated operator that acts like an if, but that produces a value, and it's the ternary operator. In this language, there's no such thing. There's just an if statement or an if expression, but they're all the same. It's just an expression followed by a semicolon if you don't want to care about the result, or not followed by a semicolon if you do. And so the if expression is if followed by a condition. Like I said, it's just an expression without structures, then the block, and then an optional else branch, which is why you have the question mark here. The else branch is just else with another block, or else followed by another if expression. So that you can do else if and list them like that. So you can do like else if C and continue your, what the hell? Yeah, anyway, the point is, this is pretty much for the important thing for the expression grammar. There's also, of course, batch expressions and function expressions that are anonymous functions that I'm not parsing here yet. But the point is, it's very simple and follows pretty much what is in Rust or other functional languages. Then there's a concept of a pattern. The concept of a pattern is not present in C. It's something that does not exist in C. The reason for this is that C is too old for this and doesn't have in pattern matching anyway. But it's a concept that exists in languages like Haskell, like Rust, like ML, like Objective-Camel, like Scala. Essentially, every modern language has that. The reason for this is it's a good thing. Even C++ 17 introduced a weak form of patterns whenever you have this tuple destructuring syntax. You may have heard of this, but in C++ 17 you can do something like this. Open bracket, x, y, close bracket equals to, for instance, something like std pair, and then I can do 1, 2. This is valid C++ 17, and what it does is it binds the names x and y to 1 and 2 respectively. It's really awkward syntax because C++ doesn't have, or wasn't built with this kind of thing in mind. It's also extremely weak because functional languages do this and have built this in a much more powerful way, because this type of destructuring is only destructuring. But in a functional language, you can do something like match a pair x, y, and I can match it with different things. I can match it with 1 and 2, do something with it, or match it with anything and 3, do something with it, or match it with anything and say, well, for the rest of the cases, do that. In other words, it's way more powerful than just a switch statement, and it allows you to do way more complicated things than just destructuring things. So patterns appear in places where expressions are captured. That's essentially the idea, which means whenever you have an expression that is produced by someone and you want to capture that expression somewhere else, like when you declare a variable, the variable is somewhat capturing the initializer, or when you pass an argument to a function, the function captures the argument that you pass to it. So this is where patterns appear. And there's a specific type of pattern that we're going to call binding or irrefutable, that is the opposite of refutable, which means that the pattern cannot fail to match. So if you recall what I just typed here, if you look at these patterns, what's important to notice is that the pattern with underscore here essentially means bind anything to this pattern or accept everything. And this is irrefutable. It's, in other words, binding, because whatever value you pass to it is going to be accepted. However, this pattern here, which contains the literal 3, is not binding, because this pattern here may fail if I pass, for instance, the value 1, 2, because, well, the second element is not a 3, it's a 2. But the pattern 1, 2 will match this, obviously, but it will not match 0, 3, or 0, 2, 0, 3. It will not be matched by 1, 2. So 1, 2 and underscore comma 3, these things are not binding. They're not irrefutable. They are refutable, in other words, which means they can fail to bind the value, which means they cannot appear as the left-hand side of a variable initialization, or they cannot appear in function parameters, because the restriction we put on function parameters and variable declarations is that the declaration has to be binding. But that's a property that the grammar does not enforce. So it's a property that is not enforced in the grammar, but by type checking after parsing, essentially. I could do this in the grammar, and I could have a special category of patterns that bind, but I'm not doing this, and I don't think it makes a lot of sense from an engineering perspective. So here, I don't have the distinction, and all I have is patterns, where a pattern is a type pattern or a non-type pattern. If it's a type pattern, it's just a pattern with a type annotation, and an untyped pattern is a type patterns without a type annotation, sorry. So a pattern is an identifier, an integer literal, a character literal, a string literal, a tuple pattern, a structure pattern, an array pattern, or a constructor pattern. And the structure pattern looks like a structure constructor. It's something like this. What this means is if we have a structure that contains the field x is equal to 2, but I can also say if we have a structure of type S and we bind the value of the field x to z, which means that z is a value that is, or a variable that's introduced that now contains the field x of the value that we pass to match. So if I do match, for instance, x is equal to 3, and I do this, what this does is essentially assigning 3 to z and then returning z. So that's essentially how structure pattern works. Structure patterns work like this because they mirror the way the expression works. What I find a little bit confusing for beginners, and you may actually find this a little bit confusing, is that the equal sign is kind of reversed. In this case, it's more like z equals to x, right? You assign z to x, not the other way around. But to be consistent with the way the structure is created, I think it makes more sense to have it like this. Or maybe with another symbol, maybe this. I'm not sure yet. So right now I just keep the equal sign, but maybe later on I change this. Who knows? Anyway, it's not so complicated. In Rust, it's a column and it mirrors what the initialization does. So I think it's also important for consistency to do something similar and consistent, which I think is probably the way to go here. And then there's a constructor pattern, which is a pattern of the form of a path followed, so like s.b followed by something like x, y, which essentially captures an object of type b constructed with x and y, which could be an enumeration, but it could also be a structure if I allow structures to be declared with parentheses as well. And then there's a tuple pattern, which is just a pattern list constrained with an open parenthesis and closed parenthesis. And then there's statements. A statement is just either one of an if expression or a match expression or loops, or an expression without if or match followed by a semicolon. So the reason for this is that regular expressions like a plus equals 1, that's an expression. It yields the value of a after the assignment. But when it appears as part of a statement, it has to be followed by a semicolon to say, I ignore the result of this thing. I don't care about the result. But I don't want to have to write a semicolon after an if, right? Because that would be annoying. I would have to write a semicolon because I ignore the result of the if. The if here types as void anyway, so it's an empty tuple. But I don't need that result anyway. Void doesn't have an interesting value to care about, so writing a semicolon at the end of this is a bit strange. I want to be like Rust, so I want to allow this syntax here and say that whatever appears after that is also a statement, so I can do a plus equals 1 after that without having to write a semicolon. So that's the idea, and basically statements are like this. It's an expression without if or match, or loops, or if or match, but without the semicolon. That's it. So we have explained the entire syntax. I think it makes the parser maybe clearer, hopefully. And now that I've explained how grammars work, I can explain how we're going to parse it. So this grammar that I've written here is LLK, and it's an important property. What it means is that it is essentially designed to be left-leaning in the sense that you look at things on the left of rules. In other words, you're only going to look at the left part of a rule. You're going to look at this part. You're not going to start expanding things that are on the right-hand side of the rule. You're only going to start expanding what's on the left, which is why we call them left-leaning. Now, the K here stands for the number of tokens that we need to know in advance. It's some look ahead. And the term look ahead is essentially the number of tokens that you're going to have to know before making a decision. In other words, if I see bool, I know I'm looking at the primitive type. I just need one token to know that. But sometimes I may need more than this to make a decision. In practice, the grammar I've listed here is LL1. The grammar is LL1, but as you add more things to the grammar, you may transform it into an LLK or an L2, L3, L4 grammar. And at this point, it makes sense to design the parser such that you can change the constant easily. And that's what I've done. So in the parser, I've actually made the look ahead a constant that I can change, and the parser still works the same way, except that you have more look ahead. So in a sense, it doesn't really matter what the constant is, as long as you know the constant. And the constant, like I said, doesn't change, it's a constant. So you could just have an array of look ahead tokens, fill them as you go, and then make a decision upon the n first tokens as long as n is lower than the k. Then there's the question of what's the result of parsing? Because I've talked about parsing, but what do we really produce, right? We produce what we call an AST. The AST is what we call an abstract syntax tree. It's like the name suggests, a tree, and it represents the syntax of the program. The reason why it is a tree is because there's this relationship of ownership between parts of the language. For instance, if you remember the expressions, I have removed this here, but if you recall, I had something like 1 plus 1 multiplied by 2. And as you can see, there's some kind of ownership here, right? There's the ownership, there's this multiply node here that has this right-hand side, a 2, and as a left-hand side, there's another expression which is 1 plus 1. And 1 plus 1 is also another expression, which is a plus, with a right-hand side that is the number 1, and the left-hand side that is, it's actually not easy to do, another 1. So this is kind of a tree already, right? And the same holds for functions, right? The function, if you look at the function fun deco, that's a function followed by an identifier, followed by a type parameter list, followed by a tuple pattern, followed by a type pattern, followed by the body of the function. So a function is like a node of the tree, which has one edge for the identifier, one child for the type parameter list, one child for the parameter for the parameter list this time, not the type parameter list, and one edge for the return type and one edge for the body. So it's really nice to represent this as a tree. It's very natural. Now, if you look at the implementation of the AST, it looks like this. So first of all, I have these macros that help me to generate the parser. First of all, these macros contain the operators here, and the operators are declared as a list, as is explained for the lexer. The principle is simple. You declare a list by creating a macro, which takes a function macro as an argument, and then you pass the elements of the list to the function. And this allows you to use this list in different contexts to instantiate that list with different functions f. And for each element, you give the name of the arithmetic expression in this case, the precedence, the token that corresponds to it, and a string that represents the actual content of the operator. And then you do this for all the operators. You have this you then group them as binary expressions, as assignment expressions, as prefix expressions, where priority is not, or precedence is not a thing because they are just parsed separately. And then there's also a list of primitive types. And finally, we have the list of AST node tags. So the types of AST nodes that we may have. There's an error if you have a parse error. There's the entire program. There's a name, which I'm using when you declare structure fields. There could be several names followed by a colon, if you remember. So I have the name just for this. I have a type parameter. I have path elements, a path, a tuple type, array types. I have literals here. I have function declarations, constant declarations, and so on. So this tightly mirrors the syntax file. I tried to make the name similar to make things simpler to understand. Then there's a list of expressions, again, trying to mirror the expressions I chose in the syntax file. And I grouped them also a bit like the syntax file. So you have the declarations, the expressions, the patterns, and also loops that are statements, so on and so forth. And then you have the type of the AST node itself. The AST node is very simple. It's a structure containing the tag, which determines which type of thing it is, and the location in the source file, so that I can report errors, both while parsing, but also later on when I'm doing name binding or type checking. This just indicates where the beginning and end of the syntactic element I'm looking at. Then there's a next field, which is used for lists. It's a pattern that you'll find often in C source code, which allows you to create linked lists inside the data structures themselves. It's called the intrusive list data structure pattern. And whenever you allocate a node, you can then just link it to another one. You don't have to create another allocation to move things to that. In other words, it's a shortcut to simplify both the allocation, both in terms of performance, but also in terms of code, because you only have to allocate the object. You don't have to put the object into another allocation, which is then linked to some other thing. I don't have to create a container for lists. The list is inside the object itself. Then there's the actual union here of all the possibilities, because, well, a function doesn't have the same arity, the same number of children as another node. So each node has its own element in this union. For instance, a program has a list of declarations, literal of type bool has a boolean value, and so on and so forth. So each of, for instance, a function here has a name, a parameter, type parameters, a return type, and the body. Of course, the return type being optional can be null. The type parameters can be optional, so they can also be null, and so on and so forth. Then there's some useful functions. So a function to print it in a nice way on the output. A function to dump it, so that's for debugging, because when you call print, you need to have a formatting state. And if you're in a debugger, you don't have a formatting state. So having to dump an AST allows you to just print it on the output without caring about allocating this object. And then there's of course a couple of properties with like whether or not the statements need a semicolon. Statements needing a semicolon are those here, expressions that are not if or match. And other properties like converting print type or AST types or AST tags into primitive type names, such as integer, boolean, and stuff like that. And the precedence, getting the maximum precedence, and also returning the precedence of one operator, which is, again, important during parsing. These things are generated automatically. So if you look at AST.c, precedence is generated automatically. Max precedence is also generated automatically. And while you may feel that this is a bit inefficient because, well, you have, for each and every expression, you're going to have one ternary operator, one comparison. In practice, if you compile with just a tiny bit of optimization, because everything is a constant here, this is going to be folded away and optimized away, and this is just going to be a return constant. So you don't have to worry about this being inefficient. If you compile with -0.1, this is gone. And these things are also auto-generated, so I don't have to bother about actually caring about this. This is done automatically for me because I have these lists as macros that allow me to do this very nicely. And then of course there's the function to print things. So whenever you have an expression or things like this, you have to print or extract the content of the AST node. For an if expression, for instance, you have to print the if keyword, then print the condition and put spaces before and after the condition, then print the AST that is the true branch, and if there's an else branch, then you print a space, then you print else, and then you print the false branch with a space before it. So that's the idea here. It's very simple code, just prints the AST node depending on the AST node type. It's a bit long though, because as you can see, there's a lot of AST nodes to take care of, but it's rather okay, I would say, in terms of length. A lot of this thing can be simplified by using functions like this, which essentially try to factor out similar parts of the syntax. And that's going back to the point I mentioned earlier. You go back to this syntax and you look at type declaration. Okay, struct declaration. A structure declaration is a structure followed by an identifier followed by a list of type parameters. And you'll see that this construct of having keyword name type parameter is a construct that happens a lot. And because of this, we can factor this out also both during parsing, but also when we print it. So it's practical to have this both for consistency, but also because writing the compiler is also easier. So it's just things that are important. And I think consistency is extremely important in language design. All right, so this is for the printing. Now for the parsing. The parser is, or maybe I should go first to the header file. Okay, this is the header file. The header file contains the declaration for the parser type, which is just an object which takes a lexer to perform lexing. That has been already discussed in the previous video. Then there's a memory pool to allocate the AST nodes. There's some helper previous end field, which holds the place where the parser was previously, which is useful to report errors. And then there's the look ahead. And look ahead, as you can see, is set to 3 here. But that means there's 3 tokens of look ahead. And tokens are really tiny, so there's no need to worry about the size of this data structure. Then there's a function called make parser, which creates the parser. What's important to see here is that I've chosen the convention to use the new object, like new underscore the name of the object whenever I allocate something, which means that there must be a free function, free underscore object. But in the case where I don't allocate things, I just have a function called make, and that means you don't have to free it. It's a convention that I'm going to observe throughout this code base, but I think it's important to highlight it because it helps the understanding. So make parser here means that I'm creating a parser structure that doesn't need to be destroyed, and we have also functions here to parse different things. In practice, the entry point is this. We parse the program. We don't parse a type or an expression or a pattern. We parse the entire program as a whole. So the client will call parse program. I've listed the others here just in case you might want to just parse a type for whatever reason, but they're not so interesting. Then if you go to the parser, make parser just creates the structure, initializes it, and then reads the look ahead tokens from the lexer by calling advanced lexer. That's all it does. Then there's of course a couple of helper functions to create AST nodes on the memory pool, like this one here, make AST node. You'll see it everywhere. If I go back here, it's just a function that allocates an AST node, copies the argument, and then sets the file name of the location such that, and the position on the file such that the AST node is written to start at the position indicated by begin and end at the position when the parser ended before parsing the last token. So that's basically it. And now let's say I want to parse something like something rather simple. Let's say an if expression. So if I look for if expr, I find this. So the way it works is very simple. You first get the current position of the parser. This is helpful because you're going to need it to create the AST node. Then you eat the token. What this means is I'm skipping it. I'm just advancing the state of the parser. If I go to the definition of each token, I'm going to see that all it does is check that the token that we currently have is the one I'm passing, and I'm skipping it. And then I also have this void here to avoid warnings in release mode because the tag would not be used because the assert would be gone. So all it does is a fancy skip token, and skip token is just calling the lexer to move to get the next token. So what it does is it moves the old tokens ahead. So you basically have the token at position 1 that is put at position 0, the token at position 2 moved at position 1, and then what you put at position 2 is what the lexer gives you. So it's like a first in, first out kind of thing. Now, there's also another function called accept token, which is just the same as accept car, if you remember the lexer, except that it does this in tokens. So it just looks if the next token is the token you give it, and if that's the case, it advances the state of the parser, and if it isn't, then it returns false. So it's rather easy. And if you go back to the if expression now, what you see is that you just eat the if, then you parse the condition, so it's an expression without the struct for the reason I mentioned earlier. Then you parse the block where the expression is true by saying parse a block expression or an error. This means that sometimes you may have someone that writes something like if C2, or someone writes something like this because he thinks this is like C. It's not like C. In this syntax, we forced people to write a block expression. So if you don't have a block expression, we want to emit an error. Right? So if you do this, this is an error. Or if you do if C foo, that's not accepted in this language, in this grammar, and I don't want to accept it. So that's why I have this construct here that errors if this is missing. Then I look at whether there's an else branch or not. So if we accept the token else, if we see else, then we accept it, and then we parse the false branch. And the false branch, if you look back at the syntax, what happened? If expr. That's because the thing was minimized. So we have if the condition, we parse that. The block expression, we parse that. Then is the else branch. So if the else branch is here, which we know whether there's an else at the beginning or not, as you can see, then we either parse a block expression or yet another if expression. So going back to the parser, this is exactly what happens. If we have an if, then we parse an if expression. Otherwise, we parse a block expression, or an error if this is something else than a block. And finally, once we have that, then we create the AST node with the parser. We allocate it through the mempool. We say that the beginning is the position where we started parsing this, and we say that the AST node should be of tag if expression, and the if expression field should be equal to a structure containing the condition set to this condition, if true to this, if true, and if false to this, if false. So that's very simple. And you'll note that this syntax here is actually legal C. It's legal C code, so you allocate a structure object locally, and then you capture the address of it. That's legal C. If you didn't know about this, this is completely legal. This creates an object with local lifetime, and the lifetime of this object, contrary to C++, is not up to the next point. It's essentially the execution of the current scope. So this object here is tied to the entire scope and actually exists until return. Right, so that's basically, I think, it for the if expression, and I think should give you a good idea of how parsing works. Now I'm going to look at adding a feature to the parser. So if you go back to this, we're going to add attributes to the AST. What this means is if I have something like a function, maybe this function is small, right? Maybe this function is tiny, and this is the case here actually. What I would like the compiler to do is to inline this. So maybe I want to have an attribute that allows me to say that. Maybe I want to have an attribute like something like this. Something like this, perhaps. In this language, I'm going to introduce the concept of a filter later on. We're not there yet, and it's a bit too early to talk about it, but we're going to have something way more powerful than using an annotation like this. But regardless, there are other attributes that are of interest. Some that might say things like import this function from C, for instance. which would be saying that this function comes from C, and yeah, there's no body because it has to be coming from some C code. So this could be really nice to have, right? And to do this, I need to add the concept of an attribute. An attribute being something that starts with a dash, followed by an open bracket, and a closing square bracket. And then inside of it, so if we look at the grammar, it will be something like after is an attribute that starts with a dash. And then we have an open bracket, square bracket, then a closing square bracket. And we have adder, something like this. Maybe I should call this adder list. And there should be adders, and adders is essentially one attribute, or one attribute followed by more. And then I can say that an attribute is either just a name, so identifier, or it's an identifier followed by parentheses for the arguments of the attribute. And then inside of it, I can say there's another set of attributes or its identifier equals literal like this, or I also allow string literals and floating point literals, why not? So here we essentially allowed things like this. Foo, that's allowed. Import, that's allowed. Import foo bar, that's allowed. Foo is equal to free, that's allowed. Bar is equal to, that's allowed. And yeah, essentially I can even nest this. So I can say import foo, bar, and faz with another list of things. That's a valid attribute here, at least accepted by the grammar. So this is what we're going to add to the syntax file. So I go back to the syntax file, I say in 5 main categories, because of course it's more than that. So a little bit of text, so attributes can appear before declarations to modify their behavior. So basically that's a small description. I hope it's clear enough. Now I need to add this to the AST. So I go to the AST and I say, well, I need an annotation. So here, if I look at the declaration, I say fun deco. I could add the attribute here, right? But then I would also have to add it to other declarations such as constants or structures or enumerations. That can be quite tedious. And maybe if I want to extend this at some point and add this to other syntactic elements such as expressions, for instance, or if I want to add this to statements or blocks, I won't be able to do that. So what I can do instead is to say, well, I add this here as an attribute list. So now every node can have attributes, and yeah, that's enough. So now what I can do is add this as a type of node. So there's I need something like to represent the attribute list. So something like this, the attribute list here. So I need something that contains a list of attributes. It's not so hard to do here. I would do ist attribute list, right? And I need something to be the attribute itself. Ist adder. All right. Then I can add this. I think it was after literals, so I can add this here. Struct adder list, and that would be something like est node adders. It's the list of attributes, and I can do struct adder, which is just one attribute, and I can say, well, the attribute, the attribute can be of different forms, right? Everything starts with an identifier, and then there's either a value or no value or a list of attributes. So what I'm going to do is I'm going to do, well, first off, there's a name. That's for sure, for every case. Then there is a list of attributes, so AST node adders. But this thing may not be there, so I also need a way to say, well, there's literal. And the way I can do this in several ways, but one way I can do this is basically by expecting the shape to be different. So either the attribute here is the value, like a literal, so it could be linking to a literal node. And if that's the case, that's fine. Or it's an attribute, in which case we're in the case where it's in fact an attribute list. We're in this case. So in other words, this attr field can either be null, that would be the case where this is null, here. Or it could be in the case where we have a literal, which is either one of these, or it could be the case where it's an attribute list, in which case it is a node which has a tag attribute. So I'm going to call this val. And then I'm going to show you how this works in the parsing phase. So at this stage, what's important to know is we don't have yet a token that is corresponding to the dash, this hash symbol here. Right? So we go there, we add it in a list of symbols. We do f hash is, well, the hash. Bam. Now I need to add this to the lexer. So I'm adding this here. That's as simple as this. Then I go to the parser, and here I want to write a function that parses attributes. So I need to know where literals are, so that I can parse these things. Int literal, float literal, and we're here. Static, inline, AST node, parse, adder list, parser, parser. So here I'm going to get the current file position. And I expect this thing to be called when you have a hash. So I eat the token. It has to be a hash. If you're calling this function, it's because you've seen a hash symbol. Then I'm going to say, well, the next thing I want is the open bracket. So this. Then I'm going to do, well, I'm going to parse a list of attributes. So I'm going to do AST node attributes. It's equal to parse many, parser. And I'm going to say the thing that marks the end of the list is token r bracket. That's the end of the list of attributes. And what separates each and every attribute is a comma symbol. And to parse one attribute, you need to call this function called parse adder, which I haven't written yet. And then I expect the token to close the list. And finally, I return a node made of these things. And then I have to say adder list dot adders is equal to adders. All right. Now the only thing missing is to write this parseAttr function, which I'm going to do right now. Now I need to produce this attribute. Remember that it starts with an identifier, so I'm going to do something like this, get the current position, then say I read the name. That gives me the name. Then I need to look at the next symbol. If the next symbol is an open parenthesis, then I know I have a list of attributes. If I have an equal sign, then I know I have a value, like a literal. And if I don't have any of these things, I know there's just a name. So if accept token parser token L parent, this is when I have a list of attributes. So I'm going to do something similar. Token R bracket token comma parseAttr. All right. And now I can say return make st_node parser begin st_node. All right. I also need to set the name. I made a mistake. Attr. Now I have to split the lines to increase readability. There we are. So now I accepted the left parenthesis, produced an attribute list, and packed that into an attribute. I need to do the same, but in the case where we have a literal. So if parser ahead arrow tag equals token int literal. Now I need to produce another node, but this time having an integer literal, so I'm going to do the val is equal to parse int literal parser, no, val. Actually, I'm going to make this way simpler. I'm going to do st_node val is equal to null. So I'm going to factor out the part that creates the node, because this would be otherwise in each and every case. So I put it out. I say the value is this. Initially there's no value, but if we have an integer literal, then I say that the value is, sorry, I need to parse the if accept token parser token equal. Yeah, you need to see the equal sign before. Then if I see the equal sign, and if I see that the next thing is an integer literal, then I can say, well, the value is the integer literal, simply. I can even do something like this. Switch parser ahead tag. So we set an integer literal, character literal, a string literal, and what about a floating point literal, and also the boolean literal? Maybe I forgot. Yeah, I forgot that. So let's allow boolean literal. All right, so we allow boolean literal. And now I have to make this switch statement slightly less annoying and more correct. Yes, token boolean literal does not exist. It's either true or false, because these are keywords. If I say token true, that would be the way to go. And then it should be token false. case or a default case, because it could be something else if the user did something insane, at which point I need to say val equals parse error. I mean, I have two ways to handle this. Either I can say, well, the next token I'm not touching, and then I'll leave it at that. Or I can say I eat it and I emit an error. Like the first option emits an error immediately, but you eat the token and then maybe it was part of something else because you forgot to close the parentheses or something. Or maybe I just leave it at that and do nothing. It's the simplest way. But that, if I do this, this would allow me to write equals and then nothing and then a semicolon, which is not okay. So I need to say something like val equals to parse error, parser attribute value. That should basically be it, more or less. Now the only part missing here is that we are not using this at all right now. It's code that is just not there, not used anymore. Or not yet used, sorry. So to do this, I'm going to look at the part where we parse declarations. And I'm going to say that before a declaration, because parse decl is used when you parse a program, before you parse the declaration, maybe you can parse an attribute list. So if accept token, or if parser ahead tag equals token hash adder list equals parser parse adder list parser, something like this. Of course I need to declare it. I'm going to move this function later. And then I'm going to say AST node, or I can say something, I can do something a bit more clever than this. So this will be parse decl without adder list. And I can say AST node parse decl parser. Instead of changing the code, I can just wrap this in another function essentially. And here I create or parse the declaration. Yeah, it's a bit too much. Parse decl without attribute list, parser. And then I can say decl attribute list is equal to attribute list and return decl. That's really practical because now I didn't change much. It's pretty much the same and it should work. So if I go cd build make, actually before so there's a couple of errors, not really important. I think it's easy to fix. What I'm going to do before is I'm going to show you what the current version of the compiler does. So what I've coded so far. So if you run foo, first of all, you now have a little message if you do -h. And you have two options. One of them is to print the AST and the other is to disable color output. So if I take a file that we just saw before, so this file here, I can parse it. Test the foo. Just works. It doesn't tell me anything. Now, if I do print AST, it's going to print the AST with the print function. As you can see, it colors things nicely, so it's easy on the eyes. But if you don't like colors, you can do -no color, and you have it without the color. What's important here is that when I print the AST, I'm not printing things as text. I'm not using the source file. I work only on the AST. Like you don't need the file data to print this essentially. So this is what happens as we have the current version of the compiler, but now I want to also handle attributes. So right now I don't handle attributes. If I do something like this, what am I doing? If x, for instance, something like this, have an x attribute, it's going to complain, right? It's going to do something like this. Invalid token, it doesn't know what the hash is, and then it says expected declaration, got invalid token, blah, 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 a lot of errors. This is normal. And then you see that the AST contains error nodes, which are printed with the brackets, the angular brackets. So if I go back to the file and fix it by make, and I see, okay, I have some mistake in the AST. Ah, yes. Of course, we have a duplicate member, so maybe I could fix this by just removing this altogether. I don't need it, right? If everything has an attribute list, I could just put this into the attribute list, right? It's a bit weird, but it simplifies quite a bit of things. So instead of creating a node, I can just return the attributes just parsed. And the begin is not there, which is a bit annoying, but I mean, that's life. I just lose the information about where the hash was, which I don't think is so important anyway. So I don't have an AST node that represents this. I just have a list of AST nodes for each and every element in the list, which I think is okay, to be honest. All right, so we parse this. Maybe now it works. Exactly, it does work. And bam, it works, except as you can see, it's not in the output. We just don't print this information yet. So what I have to do is to print it. To do this, I go back to the AST, this file, and I'm going to implement a small function to print an AST or an attribute list. So I'm going to do something like static inline void print AST or attribute list. You know, for consistency, there's this adders with an S and this attribute list. I'm just going to call that adders. It's shorter, and attribute list doesn't tell me much more than adders actually. And okay, so I can go back to the part where I'm printing it. Now I only do print many with delim, and I say state, and the beginning should be hash open. I'm separating them with a comma, and at the end you have a bracket and adders. As simple as this. And then I need to say how I print an attribute list and an attribute. So case AST adder break. I do the following if. So first of all, I need to print the name, correct? So to print the name, I'm going to do if, or maybe I do this first of all, if adders. That will help later on. So first off, I print the name. So I've done that before. I need this function here. Take the state, pass the string. The format argument is the name of the attribute. So it's adder.name. And then there's the value. So if there's a value, so it should be AST node.adder.value. Remember, there's two cases. Either it's the list of attributes or it's the actual value as a literal. If there's a value, then I do if AST node arrow adder dot val arrow tag equals AST adder, then I know it's a list of attributes, in which case I do print many with delim state open brackets, no, open parentheses this time, and then AST node adder val, and this should print all the elements of the list. Then there's the question of what to do in the other case where it's a value, a literal, in which case I just need to do the same, something like this, print with the lim, and I just do, there's nothing in between because there's only one element to print. At the end I print nothing, and before it I print the equal sign. Okay, that should do the trick. So that should be enough to print the attribute list. Now I need to tell the declarations to print stuff before their own value. But instead of putting this here for each declaration, which would be kind of cumbersome, I can just put it here, in fact, because it's common to all AST nodes. So if AST node adders, AST node adders, make, bam. As you can see, now we have the list of attributes printed before our type. Now there's a missing space here, so I'm going to fix this. There we go. And now we have everything we want. I can check it. I can check that this works the way I expect it. So I can say x, y is equal to 1 and z 1. So that's not possible. I need to say something like x equals to 1, z equals to abc. And it doesn't work. But as you can see, something still works here. What's strange here is that there's a space here, which I have to address. The question is, what is happening here with the closing bracket? Did I mistype something, first of all? I don't think I did. So, expected closing bracket. I think it's because we're not parsing something. So see, here we expect the closing bracket, and there's a comma. And if you look at parse attribute, we parse the string literal, the character literal, float literal, integer literal, boolean literal. So that's okay. Yeah, but no, this is the problem here. It's a brace. No, a parent. Oh, I'm kind of stupid. What copy and paste does to you is it's this kind of stuff. So if you accept an open parenthesis, then you parse many things separated by commas and ending with a parenthesis, then you eat the parenthesis. That should fix it. Bam, fixed. So here we have it. There's a slight problem that constants seem to be printed with, what's going on here? It's because I'm in normal mode. So constants seem to be printed with a space before them, which is kind of strange. I have to address this, go back to the printer here, and I go to the attribute. I'm printing things with a space in front of it because, well, I'm printing the space too much. Now it's fixed. So that's it. We have our attribute. And as you can see, I basically showed how to add a tiny bit of syntax to the grammar and how to change the parser to adapt it. And hopefully you have a clear idea how to write the parser now. Again, it's not really complicated. It's a recursive descent parser. All you need is to make a decision based on the current token. So you either accept it or you look at it, like in this case here, with a switch or with an if statement, and you make a decision on what to parse. It's really not complicated. And to make your grammar work correctly, to avoid ambiguities, I also explained how you handle precedence and how you design your rules, your production rules, such that they are prioritized expressions in the order you want. That process allows you then to parse things as the production rules, or essentially to write your parser just like your production rules, essentially by looking at things and then saying, okay, well, I'm either parsing a logic and expression or a logic and expression followed by something else, which means if I have to translate this rule into a parser, an LL parser, I would say first I eat what's on the left because it's an LL parser. To eat it, I would just call parse logic and expression. And then I figure, well, maybe what I have on the right is the symbol or, and if that's the case, then I eat it and I parse another logic and expression, and I create an or node with those two things. So these rules, they essentially really reflect the algorithm that parses the actual grammar. And importantly, if you design them like that, it's a bit more tedious than designing them, in the natural way with expressions directly being part of the same thing. But it enforces a certain mindset that will make writing a parser easier. And I think most people should have that. So hopefully I've explained how to write the parser enough, and I don't think there's anything else to be added to this parser. We have patterns, we have statements, we have attributes, and basically pretty much all of the grammar is laid out right now. All right, so I think it's time to leave for this video. Next time I'm planning to maybe introduce a little bit of name binding, which is the next step. And name binding is about assigning or connecting names and parts of the AST. So you're going to go through the AST, look at, for instance, the name foo, and connect every instance of the name foo where foo is visible to the AST node, which contains the declaration for foo. And that process is called name binding. And because, again, of the way we've designed this grammar and the way we've designed the language, we can do this separately. In languages like C, you would have to do this at the same time as you do type checking. But in this language, we are free and we can do this very nicely separately from the type checking. So yeah, so that's for next time. And thank you for your attention. And I hope this was instructive enough.